My name is Gavin Rock, and this is my Lab 5 Sliding Eraser Energy and Frictional Lab. So the purpose and goal of this lab, so the purpose was to explore our own physics interest and show our understanding of physics in the form of our own lab that we created. And I decided to focus on frictional force and kinetic energy relating to frictional force in my lab. And the goal was to find the coefficient of friction, the acceleration, and the frictional force alongside some of the kinetic energy and thermal energy aspects based on initial conditions that we found in Tracker during the lab. So for the models and results preview, so we used two different models. Tracker was used to calculate the initial conditions for the lab, and glow strip was used to determine the final results of the lab and to model the simulation. And based on our results, we found that we can find the forces act upon the dry erase eraser and the energy as it progresses through the simulation. And we also can show our desired outputs based on the initial condition of the experiment using the formulas that we needed to. And key physics concepts, so we use Newton's second law, force equals mass times acceleration, and this also helped us derive what acceleration is based on our equations on the right side, and we also use the kinetic energy, or the energy principle for kinetic energy to equal E thermal, and because the kinetic energy final for this lab is 0, we can just have kinetic energy initial is equal to E thermal, and then we also use velocity update formula and position update formula to model the simulation as the eraser moves across the x-axis. For a free body diagram and initial conditions, so the system is the block and the surroundings of the floor, earth, and all the environment around the block. The forces acting upon it, F normal and F gravity, cancel out. Force of friction is constantly acting on the block in the negative x-axis direction, and the force applied is only initially applied before release in the positive x-axis. And then the initial conditions were that the mass is 0.027 kilograms, initial velocity is 1.2 meters per second, the change in x is 0.437 meters, and g constant of gravity. So for our experiment and results based on tracker, so we had the object tracking where we found that it was going from the left, the negative axis, x-axis side towards positive x-axis, so positive motion, and we tracked it as the object moved across the x-axis. And on the right side with the graphs, we can see how it initially had a faster velocity initially, and eventually slowed down to 0 velocity where the object stopped at. And then we can see with the data table what the initial velocity was, the final velocity, and also what the change in x was during the lab. For our coding aspect of the computational model, so we derived the acceleration coefficient of friction equations earlier in the lab, and then we have the forces equations to calculate those acting upon the block. Then we also have the energy principles and energy equations to calculate the kinetic energy and thermal energy in the lab. And then we also use the velocity update formula and the position update formula to calculate where that is based on the simulation and as it goes on throughout the simulation. And then we also have the energy update formulas on the right side. And then on the bottom we have how we printed out the text for each of the values that we found at the end of the lab. And for our results, so just after the beginning, the kinetic energy was much greater than the thermal energy. This is because the object had moved very little, so it still had a higher velocity. And once it gets to the end, there's going to be no kinetic energy because the velocity is 0, and all that energy will have been transferred to thermal energy. And we can see that the energy principle is satisfied because the total energy is constant throughout the model. We can also see with the results that we were looking to get, acceleration is equal to negative 1.65 meters per second. Coefficient of friction is equal to 0.168. Force of friction is equal to 0.0445 newtons. So the overall frictional force is quite low, and E thermal and kinetic energy are equal to each other, which they should be based on the energy principle. And for discussion, so the kinetic energy of the block is fully transferred to the thermal energy when the block comes to a full stop, showing the conversion from kinetic energy to thermal energy based on the work of friction. And the simulation predicts which shows the output values for each of the important values we were looking to solve for. And we found that the frictional force, coefficient, acceleration, kinetic energy, and E thermal could be solved for using given equations, and the original values found using Tracker. And this lab helps us demonstrate the use of the energy principle, Newton's second law, and other physics equations to find desired values from a set of initial conditions found for an experiment. And for the errors that may have caused slight calculation differences between the real world example is that the constant friction assumption may not always be true because parts of the surface may have different levels of roughness to them. Other forces such as air resistance are ignored. Even though these would make up a very tiny amount of force on the object, they still should be accounted for, which might cause a little bit of an error in the difference between the actual forces acting upon the object and what we calculated. And these errors can be very minor. for the what if and what does it mean question. So the what if question I created was, what if the coefficient of friction was doubled? How would this change stopping distance and thermal energy produced? So the larger coefficient of friction means that there would be a larger force of friction acting upon the object, and the block would therefore have a shorter stopping distance. And then also the thermal energy per unit distance would be converted faster from kinetic energy, but the total energy converted would still remain the same. And for my what does it mean question, what does it mean that the thermal energy that is gained by the object surrounding equals the kinetic energy that is lost by the object? So this essentially means that the energy is conserved and that the kinetic energy is transferred into the surroundings in the form of thermal energy. The energy is actually not lost, it's just lost or transferred to the surroundings. And this ensures that the energy principle is satisfied. Thank you for listening.